Perfect. Hello, everybody. Leave some time for people to jump in. Okay, so today what we're going to do, I think it's the last hard problem set that I have to do in the linear algebra category on this website. I did this one last time. I struggled for kind of 2 hours. Actually, it was 3 hours, but we got it at the end of the day. I just didn't resubmit it. The last one I had that is hard is this one, the conjugate gradient method. So we're gonna try our best to kind of get it done. This is kind of like a stochastic gradient descent type of variant. Not exactly that, but it's kind of the same structure overall that we're looking like. And this will be for solving linear system of equations. So to find our x given like a transformation matrix A. So that's that. Before we get started, I'm just gonna make like a small overview of this thing. I've been using this for quite a while. I know the guy that actually made it. Big fan. And I'm using it to kind of like practice problems, right? So this is a whole website made just for machine learning and kind of data science problem, kind of a lead code type of thing, but more heavy on the theory, and then you have to implement something in order to get to pass. And there's like multiple categories here. There's linear algebra, there's like NLP here, deep learning, probability, the usual stuff that you will see in machine learning and deep learning. Kind of a good supplement, I would say, to your deep learning kind of a study session, really. So, but in my case, I'm trying to clear up as much as possible the linear algebra stuff. We're gonna start with this. How this works is like, this is kind of a place for beginner to kind of come and ask questions about anything related to machine learning and deep learning. So there's no wrong question. There's no things that are too beginners, right? You can come in, chat with me about like what you're studying right now. If you want to hop along with me and try it out for yourself, I'm gonna leave the link into the chat. And yeah, it's kind of your weekly reminder to go ahead and study that stuff and machine learning and deep learning in general. How stuffs are ongoing right now. I think like I believe that like a very solid understanding of like how these machine learning models are behaving and working underneath will be kind of an advantage going forward. If you understand like how this tool that is used by millions of people is working at the intimate level, I think you have an edge. No, irrespective of like your field of work or study or whatever. As background for myself, I have kind of a more research / entrepreneurship background. I was in computational neuroscience doing research on that type of stuff, right? So I was leveraging machine learning in order to kind of gain insight in the brain. I was mostly working on consciousness. My thesis subject during my PhD was to try to detect consciousness in people that couldn't speak or move properly, right? You didn't know if they were there or not, but they were not dead, right? So this is what I was doing, and I have a few papers out there. And these days I'm mostly working in my company that is doing supply chain intelligence, and we're leveraging AI engineering, LM, that kind of stuff. So with that being said, let's try to figure out what the hell is the conjugate gradient method. Linear system, we all know what's up, right? It's not something that is too outlandish. This is not too difficult. Like the usual shape that you have is you have multiple of these, right? And then the thing that you have to figure out is like the variables, right? So that's the game of a linear system that you're using. The A's and the B's here are like our transformation matrix, and then you have your vector X. Like here it's like X and Y, but like you have multiple X's, and then you try to figure out like what X's that you can put there in order to get to here is the constant C's, but like it can be anything really. So that's kind of the game that we're playing here, and we're gonna try to implement what we call the conjugate gradient. So when you get something like this, try to first, I like to lay the land a bit and figure out where I'm sitting at, and then I dig a bit deeper. And I'm always there, right? So yeah, let's hope this one will be easier than the last one. I'm always the guy that is running the website. Okay, cool. So let's read what's up over here. So our task is to implement the conjugate gradient method for solving linear system. And okay, the conjugate gradient method, an efficient iterative algorithm for solving large, sparse, symmetric, positive, definite linear system, right? Every time you see if you're working in a algorithmic type of setup, sometimes what you're gonna see is that there's techniques that are widely used, right? And then there's other techniques that seems to be more performant, right? And then you might wonder like why they're not widely used. It's because there's a lot of let's say asterisks in how they can be used. Otherwise they can't, right? In this case, like the matrix need to be of a certain type in order to be used. So when you're gonna research a bit conjugate gradient, you're gonna come up with like, hey, gradient descent is doing this, but then conjugate gradient is doing this stuff, right? And it seems to be just literally an improvement over stochastic gradient descent and these type of things. But it's because they have like a very strict set of parameters. Yes, I got the shirt. Like here, this is good. Yeah, going deep. Let's try to go as deep as we need in this step. Okay, wait. So okay. So we have to write this. We have our A, which is our matrix representing the linear system. And then we have our vector B on the right side of the equation. And then we have our maximum number of iterations. So this will be like the loops that we're going to get in order to try to do multiple guesses. This is an iterative algorithm, right? When you have an iterative algorithm, you're going to do a bunch of guesses. And then you're going to go and go and go. And then as like every time you have an iterative algorithm, you also have something that tells it to like stop, right? So here in this case, I think it's tolerance for stopping criteria, right? So you have a tolerance here, usually close to 0, but never at 0, right? Because how it works is that you're gonna get the you're gonna make a guess, right? And then you're gonna check if the guess is good, right? And then you're gonna get the residual of how far you are with the guess, and then that residual is what you're gonna check if like, okay, is it small enough now? Can I stop? You never go for like exact solution usually because you will go on literally forever. Okay, so we're already kind of starting to see kind of the shape of what this thing will go. So what I'm seeing here is that there's kind of a shape like this. Like in here, this will go from like 0 to at most n right here, something like this. And then this is kind of inside, and then in here there's gonna be something that we're gonna be able to check right over there, and otherwise you just continue like this and then go back there, and then this is gonna go here. It's kind of this shape here, and this shape is dictated, this exit criteria is dictated by the tolerance that is over here. Right, so there's something called the tolerance. There's our n that sits over here, and if we're out of here, we're still gonna need to return something, right? So this we're gonna return anyway, and this is dictated simply by n. So most of the cases when we're gonna debug, we're gonna fuck it up and go over here, right? That's gonna be mostly what's gonna happen in I would say 90% of our thing. Okay, so we're making headways. And then we have our initial guess for the solution vector. At the beginning, you can say it's none. Default is 0 vector. Perfect. Yes, this is perfect. This is good. And then, wait. Okay, right hand side vector. Okay, so we have this example. So we have our A's here. These are our B's. And then we have to find our X. That will give us our B's basically. So this is the first, and then this is the second, and that's what we're gonna give us this for this one, and this for this one. Okay, cool. Okay, so let's learn a bit more. Okay, the C gradient is often applied to the quadratic form of a linear system, AXB, and then we have this thing which gonna give us what? I'm not sure. Is used to its differential reduction the following for a symmetric A. Okay, the conjugate greedy method use search direction that are conjugate to all the previous search direction. With search direction A are orthogonal. Okay, so this P is our search direction, right? Okay, yeah. This results in a more efficient algorithm. It's ensure that the algorithm gather all the information in a search direction at once and then doesn't need to search the direction again. And this is our residual vector, and then like we have a whole bunch of variable that we're gonna need to inject in there. This is the step size. Okay, this is this big ass. What do we have? We have our residual. Okay, and then we have what we have. This is our residual vector, and this is our P. This form, I remember this form. I think that's the form of the conjugate. And then we have our A over here, right? And this is the residual is there. Then our X, this is how we're gonna update. So this is what we need to calculate, right? The alpha need to be, it seems to be important. So okay, there's two steps. There's the initialization step, and then we step into that stuff. Right, so we're gonna go kind of here and do a bunch of stuff, and then we're gonna do the rest. Okay. Right, so here we're over there, and this is our K is in there. Okay, so far so good. I think it's not too bad, right? So this I understand, right? We have our initial guess. This one will be all 0 at the start, right? This is what we said. This is what we said. Where do we have this information? Default is 0. Yeah, okay, perfect. So this is all 0 because like we literally set it up to 0 here, right? So what I mean, like when I say that, like I like to, before doing anything, I like to kind of just have a good view of the stuff. So here, this is what we mean, right? This is the 0. I think you can put whatever you want. I think there's maybe better default, right? But I'm gonna stick to that. Then we calculate the residual, which is B minus A. It's gonna be B, right? Because it's gonna be all of this stuff minus zeros. Okay, and then P is gonna be our residual. Nice. This is where we're gonna do the heavy lifting. So this is important, right? It seems to be like what's driving the whole thing, right? And then we have our next X at K plus 1, which is the previous X that we had, right? So this is the previous iteration plus a at k, so this one that we just calculated, times pk, and pk is, it would have been nice if we could have defined them a bit better. Like p is never defined. Yeah, it's defined here, is it? Search direction, I think this is what it means, but what is the, how do I update p? Okay, this is p0 and it's this, and then at 0, okay, all of this will be 0, and then I get that, and then I update p at the end. So p is already updated. Okay, cool. Get it. This is good. We already have p because it was updated prior, and p is equal, so our p is over there and is equal at k, right, is equal to the r at k plus a beta k, which is this thing, multiply, sorry, inner product of pk minus 1. Okay, so these ones are just gonna be set up for the next iteration. Okay, it's a bit weird. Okay. No, I think it's okay. I don't think it's that weird. Then because this is a setup again. What I'm saying here is trying to understand the orders, right, for this thing. So because I'm gonna have to put stuff in order in order to kind of get the right thing. This is the first thing I'm gonna do. This only required the pk that was already set prior. RK was set prior also. And then what I'm updating here is what I need for the next iteration. But this one, I can't group the BK and the can't group the alpha and the alpha and beta together, because the beta for this K require the R for the next iteration, which is a bit confusing here, because I think we're kind of looking ahead a bit. And this is where we're gonna stop, right? We're checking RK plus 1. So the next residual, if it's smaller than tolerance. So here is gonna be the R that we're gonna check. R and at K plus 1. This is the thing that we're gonna tell us if we need to get out. Okay, so the actual thing that is important here seems to be these two. These are important. The rest is kind of like preparation for the other thing, and then this is what scaled the new direction for the next iteration. It's kind of a weighted average. A momentum seems to be like a sort of a momentum type of gradient descent algorithm. Okay, cool. So let's read it till the end. Okay, so this is good. We got that. And then we have an example, I guess. So 4x plus 1, x2 equals 6. And then we have x1, 1x1 plus 3x2 equals 6 again. And then we initialize with 0, 0. And then we go and then we get the residual b minus all the transformation matrix x0. Okay, yeah, that's our guess. Okay, it's a bit this is a bit confusing. This with x1, x2, it's a bit confusing. I don't like this notation. because it looked like this is an indices prior, but I understand. Okay, perfect. So this is x01 and this is x02. So we get that, and then where a residual will be b minus these two multiplied, and p0 equal r0. And the first iteration, we calculate all of this. Good. And then we update our solution. So we go x1 equal, well, so our guess of x, let's say x at here, right? And then we get that, and we do the 0 stuff that we have at the start, plus our alpha that we found over here, okay, which is a step that we're gonna take, and then this, which is our residual, right? No, it's not the residual, it's the p0, which is equal to the residual. Okay, good. Then this is our guess, right? This is our guess for right now, and then we update the residual, and the residual is what is telling us if we're right or not, right? Yeah, it's telling us if we're getting a bit closer to if it's right. And then we compute the beta. The beta is the scaling for the new direction. So taking into consideration, okay, yeah, okay, this I get. So B0, R1, R1. So this is just messing up with the residual, we get that. And then we update the search direction with the P. And then you will update it in both this direction and then this axis and this axis. So this will give us, this is our residual at 1. So this is what we just calculated. Plus beta here, and then it was just going to be a bit bigger. And repeat. Okay. Why do we stop? Okay, so this we need to calculate. Okay, the what's it called? The dimension. The magnitude of vector, yeah. Okay. Okay, perfect. So if the magnitude of the residual is smaller than the tolerance, then it's good. So if all the r's are very, very small. Okay, I think I get it. Honestly, I think I could do it pretty easily. I think the only issue I have is why this works. Okay, so here there's a visual of the two method. Yeah, by the way, I haven't coded anything for this power. I'm all doing it right now completely blind. I did check some video about the conjugate gradient, but I haven't tried to code it in any shape. So here is okay, so the green is what? So this is gradient set with optimal step size, okay. So this is doing zigzags, and here conjugate vector in red for minimizing quadratic function associated with a linear system. Okay. Okay, so okay, I think this is why. Okay, n is the dimension, right? N is maximum number. This should be the dimension of the matrix technically, if we follow that. Yeah, it should be, but like I think here it has a different meaning. Okay, I'll just get that. Am I sponsored by DeepLM? He gave me a T-shirt. So no, I'm not sponsored. Really, I just really like this this website, to be honest. And yeah, like I've checked out the website when it was first announced on Hacker News, because I was starting to think about some, like, either making something similar or just doing more lead code with machine learning in it. But Mo actually did it, and I loved it. There's a lot of new features that are being added continuously. So there's like the notebook mode over here. There's a whole bunch of stuff to help you out while you're going through the stuff. So I'm kind of consistently going through it. I'm having this whole series, which is we are going back to linear algebra and trying to study it in like many different ways. But I was looking for something really that had the theory and then the kind of the code stuff. Yeah. So yeah, not sponsored. Mo, if you would like to sponsor me, that would be nice. I would love that. The website looks more similar to CodeCrafter without the Git repo. Yeah, I've heard of CodeCrafter actually. I think it's another pretty nice setup. I think in their case they're very focused on like huge project. If I remember correctly, I think they were like you can like build your own compiler and stuff like that. Yeah, so guys, if you're trying to learn like stuff in depth, either algorithmically or like a project or like a concept, from my perspective, the best way to do it is really to kind of go into the internal of the thing and then try to implement it yourself. It's not that useful in order to put it into production, because you will never do that. You will rarely do that. You will rarely kind of make something from like scratch and then try to make something out of it. You're going to use something, right, that is already made and maintained by multiple people. But if you already went into the internal of it, your understanding about how and why it works will be so much greater, and it will be way easier for you to kind of, how to say it, like navigate through it. So for instance, like if you're doing a lot of deep learning, one area that might be a bit confusing is like the gradient optimizers, right? Like Adam W, and all this. I would highly suggest you to go ahead and then try to implement like some of them. Start with gradient descent and then walk your way through, and you're gonna see that their structure is always the same, and then there's just some things that are switched, right? And then like you can see like the Nesterov accelerated gradient, the Adam are looking very similar, but then they are in the same kind of line of optimization and how like the algorithm is made. But like there's just some tweaks left and right that was made for some particular reason. Yeah, it's very useful, because then when you go in and use, let's say Adam W in your architecture, or like you read the paper and it's this thing that they're using, it doesn't look like just black magic. You kind of understand the lineage a bit, but like you will never implement it yourself in your own algorithm. You're gonna use whatever is in the PyTorch or like whatever framework you're using. Okay, cool. So what I was trying to put here is this. So this is, on a nutshell, what we're trying to get to. But the end is not similar. So here, so I'm just going to strike it out, this part. Okay, this is not exactly the same. So this is good. And then it will do just fewer steps and go into a specific direction. And then there's this whole story about the quadratic function that I'm not sure I understand properly. So, okay, the method is often implemented in an iterative applied to sparse system. Large sparse systems often arise with numerical solving, partial differential equation, or optimization problem. Yes. Okay. Yeah. Okay. So we have this. This is our setup. So for the vector x, where the known n by n matrix A is symmetric, positive, definite, for all non-zero, unreal, and B is not well within the unique solution of the system by let's start. Yeah, so what I was saying at the beginning, like I don't know, it seems like you have to have a whole bunch of shit to align to be able to use this, which is cool, I guess, if you notice it, right? If like the internal algorithm that you're using in some of your packages are noticing that this is like a symmetric, positive, definite, real, valued kind of matrix, and then okay, let's use the conjugate gradient method, to speed our shit up. But other than that, like usually it's the simpler algorithm that kind of always win. Okay, cool. So this is good. So the A's have a very specific structure here. Okay, yeah, it's symmetric. We have 4, 1. Yeah, wait. We have what in this set? We have 4, 1, and this is the output. Okay. So my matrix A is 4, 1, and then I have 1, 3. Yeah, this is symmetric for sure. And it's positive, semi-positive definite. Yeah. Okay. And then we have our B over here. This is our A. This is the B over there. B is 1, 2. Yep, okay. And the final X that we find, so X star, is 0.09, 0.09, and what? 0.63. 0.63. Okay, so that's the shape of our stuff. Perfect, let's continue. Derivation is a direct method. Conjugate method can be derived from several different perspectives. Okay. Proving the orthogonality of the residual and conjugate C of the search direction. A conjugate refer to a binomial term that is when paired with another binomial term, only the sign between the term is different. So I mean this stuff. Okay, this is the expression, this is the conjugate, so this is the expression, conjugate. Okay. Okay, so the conjugate stuff has to do with another, it's for the polynomial. This polynomial has rational coefficient can be factored into polynomial with rational coefficient. Okay. Okay. That's the thing that I think I'm not getting 100%. Like that stuff over, is that this one? I'm not sure. There's something about a polynomial that I'm not getting 100%. Okay. No, it's a way to solve. It's not really a regularization technique. It's a way to solve for the minimum, right? Kind of like I think you already seen like that stuff, like a gradient descent type of a flow. You see, when you have that, let's say you start randomly, right, and you're trying to figure out like the bottom of a function, right? In like machine learning sense, the bottom of the function is how you're going to minimize a cost function, and then the actual function in multi-dimensional place is your model weights, right? It's kind of the idea. You could swap technically this with the conjugate if like you had like a positive definite symmetric transformation matrix, right, for your linear system. But usually it's not used that much in machine learning sense. It usually is going to be like gradient descent, like a different version of it, like Adam W and all this stuff. But the idea is that it's that thing in your cost plane that will tell you how you're going to move the weights, if that makes sense, right? Conjugate, same thing. So before that you said true always felt like algebra had a lot of jargon. It's like something like recursion, you either get it or don't. Yes, it's language, right? Yeah, it's really language. Like if you stop and think about it, deciphering it as a language that is trying to tell you something, right? That is not a thing that is written. It's a bit easier, I feel, right? So like think about it, right? It's been what 30 minutes we're here. I haven't done any coding right now. I'm just trying to understand the setup, right? Which is kind of normal, right? That's kind of how you should go about it. Like when you have a new formula that you never seen before in like a setup that you never seen before. I already know the shape. You see here the shape that I've done here. I already know what's gonna be like because it's really close to gradient descent that are already implemented. It's already close to like this type of algorithm where you have a function that you're trying to minimize some like cost or penalty or whatnot. And here I saw that it was the residual, and I know that my residual will be my exit criterion, right? Because I know the shape. I know what they are talking about. If you had no clue about gradient descent and you read that, the fuck are they saying, right? Like you will not know at all what is the there's so many letters, right? You don't know what is what. You don't know the shape also to help you guide through the setup. But they're talking about something that is a bit greater than like the little elements that are in it. Like that's the thing that you need to keep in mind with anything mathematic related, especially like with machine learning. They're talking about something that is not what the letter are saying. There's some movement in it that you need to get. The more you do it, also, the more you code stuff like this. Yeah, too many letters. The more you code stuff like this, the more you get an intuitive sense about how the movement is flowing, right? And then when you see that, you start to see a bit the movement. Okay, so blah 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 blah. We have two non-zero vector u and v, and they are conjugate with respect to a if this is equal to 0. Okay, cool. So this is their definition of the conjugate. Since a is symmetric and positive definite, the left-hand side define an inner product. So this is the inner product. Cool. Perfect. Wait. Yeah, okay, cool. Two vectors are conjugate if and only if they are orthogonal with respect to this inner product. Two vectors are orthogonal to each other if their inner product is 0. Okay, nice. Okay, to this inner product. So if yeah, perfect. This is the exact definition that we're are saying. Being conjugate is a symmetric relation. If u is conjugate to v, then v is conjugate to u, right? Because when we saw that image, right here, this example. Yeah, wait. Okay, I guess it still work. I didn't know it was you could flip them out, but I guess it would make sense that you could flip them out because of this polynomial thing. Okay, right, okay, so that's that. Suppose that we have P with a set of n mutually conjugate vectors. So here we're starting with U and V, right? Like in the image, you have U and you have a V. Here we're saying like, imagine there's just a heckload of P's instead. So P1, P2, Pn. With respect to A, then this is equal to 0. Yes, Pi and Pj, when the I and j are not the same. Form basis, and like this is everyone with respect to everybody else. Okay, right? Okay. And this X star, they were saying that it was this solution. Okay. So they are mutually conjugate vector. Okay, perfect. And the basis is that thing that we've covered last time. That help us define the whole space. So they need to be orthogonal if this is the case, right? Okay, yeah. So this is going to be alpha times our P conjugate vector with respect to A. Can sum them up. That's going to give us, wait, can we sum, is it a summation here? What are they saying? Isn't that in multiple dimension? I'm not sure here. Okay, then the A times X gonna give us that. I'm not sure why we're doing this here. And left multiplying the problem AX equal B with the vector P K transpose yield. Where is the K coming from here? It's just a random like element in this that we're selecting. Okay, equal times B. Okay, and then we're replacing the PK. We're just inserting it here, I guess. Okay, right. And then what? Okay, yeah. This part, I have no clue what the heck they're doing. That part, zero idea. Like, I get from up until here, but then, to be 100% honest, the rest, I'm not sure. But this gives us our clue for why the heck the AK is like that. So this is this one here. It doesn't have the same exact form, right? PKB. Oh, but like the B, we have. Where did we get the residual? Here. It's B minus whatever, and this is our first residual, and the next residual is this minus A. So, okay, maybe this is y. So this is the inner product between the two. Okay. So we find a sequence of n conjugate direction and then compute the coefficient AK. And I think this is what we're doing in our motion here. This is the conjugate direction. It's given by this new direction scaling. Okay, yeah. And then, okay, so I think this is like the direct method. Oh, okay, direct method. We're not doing this. We're doing the, yeah, we're doing the iterative method. Okay, yeah. So this is maybe why I'm confused here, because it's not exactly the same thing. So this is for the direct method. I'm really close, guys. Really close to coding something up. Right? Well, wait a bit. So if we choose the conjugate vector pk carefully, then we may not need all of them to obtain a good approximation of the solution x. So I'm going to regard the conjugate gradient method as an iterative method. Okay, so allow us to approximately solve system where n is large, that the direct method will take too much time. So we don't want to do this. What they're saying is that this is garbage. We don't want to do that. It's going to take too much time, and it's not worth the time versus like the accuracy that we're going to get about our solution. Instead, we start with like a garbage guess, and then we're going to refine our garbage guess. So we can assume with the loss of generality that x0, okay? Otherwise, consider system az equal b minus x0. No, we're getting this at start. So I think with x0, we search for the solution. And in each iteration, we need the metric to tell us whether we are closer to solution x star. Well, I'll just stop here. Like this is like the foundation of like anything optimization, machine learning you're gonna find, right? Yeah, like every time you're gonna read something, let's say like if you're into machine learning, deep learning, AI, whatever, right? There's a few things that stand out that you're gonna always kind of look for unintentionally when you are reading something new, right? In machine learning, like it's usually the stuff that you're gonna look for first is like, how do we know if we're getting better, right? What's the thing that is telling us that we get better? So this is why, like sometimes, let's say you read, I don't know, like the R1 paper, right? And then you're like, how do we know if the reinforcement learning is helping or not, right? GRPO, let's say the algorithm that is jammed inside for doing the reinforcement learning in the post-training. And then you realize it's code, right? Or like it's mathematic that they're using this for. You understand that like it's using some kind of metric in here to do the feedback loop. But then there's some stuff that you're like, how are they knowing if it's right or wrong? And usually this is where like it's some weird approximation, and then like maybe the model break down or stuff like that, and you can zone in into here and understand that like there's an issue on this part. But it's all on the umbrella of like, there's a metric that tells us if we're getting better or not in our approximation, right? Yeah, just a bit of information, because like there's just, I would say like there's like 6 elements like this in the machine learning or like deep learning or optimization type of material that are important. And as soon as you like go through it, everything that you're gonna see that is super different and whatever is like variation in some of the 6 blocks. So yeah, if you already implemented them and then you play with them enough, then like you know what you're gonna look for because you have already implemented them in some ways. Okay, this metric comes from the fact that solution x star is also the unique minimizer of the following quadratic function. Ah, okay. So what they're saying is that the solution, right, is minimizing this function here. Yeah, and the existence of a unique minimizer is apparent as its Asian matrix of second derivative is symmetric positive definite. Okay, cool. Okay, nice. And that the minimizer used solved the initial problem for low from its derivative. Okay, cool. So this thing is important, right? So this thing is important in some way. It's going to be important, I think, in like how it's going to be set up down there. But I don't think we're going to need to use it in order to calculate anything. Yeah. Okay, cool. Right. So first base vector P0 to be the negative of the gradient f at x equals 0. The gradient of f equal that, yes. Starting with the initial guess. This means we take P0 equal b minus, I think this is what we're doing here. Yeah, is this. We're taking that straight up. The other vector in the basis will be conjugate to the gradient. Okay. Is also the residual provided by initial step. Okay, yeah, this is what we're saying here, because these two are equal. And then RK would be the residual at the kth step, because we're saying this is the previous residual minus what we have right now, with alpha A, the transformation matrix, and PK. Here it's XK. Is it the same thing? Shouldn't be. Is it a mistake here? It says PK. Shouldn't be X, but I don't know. This one I'm not sure why it's this and not the P. Okay, I'm gonna put an asterisk to that. So watch out here. Is it PK or XK? Okay, as observed above, RK is the negative gradient of f at the function f at xk. So the gradient in this method will require to move in the direction RK. Right. Here, however, okay, right. So this is the proper residual, but what we're doing is not this, we're doing that. Okay, cool, I get it. A practical way to infer this is by requiring that the next search direction be built out of the current residual and all previous search direction. The conjugation constraint is a orthonormal type constraint, and hence the algorithm can be viewed as a Gram-Schmidt orthogonal normalization. I don't know what this is. I don't know what I don't know what the Gram-Schmidt. I should probably know it, but yeah, I'm not sure what it is. Let's find an orthonormal basis. Okay, cool, but okay, yeah, I don't know that. I don't know the algorithm either. I think I may have seen it at some point, but okay, whatever. So this is this. Give the following expression. So we have that this shape is the PK, right? Because the PK is that, and this bulky thing, is it RB? I think it's getting closer to RB. Okay. Next optimal location is given by that. So that's good. Wait, is it this? This is X. No, it's not the same. Okay. Where the last equality flow from the definition of RK. Right. Right. So this is our A. And we have the RK here. It's not exactly the same stuff. Because here there's PK at RK. And here it's RK, RK. I don't know if it's messed up or... Yeah, this one is weird. See here, it's RK, but like, shouldn't it be PK? I am not entirely sure. Let's get jump here. Yeah, I'm not sure 100% because it doesn't look like that. No, yeah, maybe it's there's a mistake. I'm not sure. Okay. For the last equality, follow from the definition of RK. Okay, the residual at K. The expression for RK can be derived if one substitute the expression of xk plus 1 to f, minimizing it with respect to alpha k. Okay, and then we get okay, it just explain how we get a. Okay, cool. Okay, cool. And I think if we go there, we're gonna start to see the exact algorithm. But wait, here it's RK again. What is going on? It's not the same thing. Am I dumb? Yeah, I'll get to you. Yeah, at life. Just give me a second, because what the fuck is going on? I don't get why we have a difference here between the two. Yeah. So, Empirical recipe by Prestel. No, I haven't read of it. I'm currently looking at the book Machine Learning. This one, Mathematics for Machine Learning. Good one. Honestly, it's a good one. It's a good handbook, I would say, right? It's a bit dense, right, in terms of like the content in it, because it's not gonna like baby step you into the thing, but it's a very good condensed element of like what you should know, and then it give you like reference about like the actual thing that will teach you the stuff. But there's exercise in it. There's we're gonna get back to doing like these type of exercise as soon as I'm done with linear algebra stuff on DeepML. But I'll take note of the numerical recipe. Actually, I'm gonna take a note here. Recipe. Okay, so we have questions. I am one of the PhD students from GP University. I'm struggling with machine learning and deep learning. I worked for it a few years ago. I usually use YOLO and MASC or RCN, but I want to know inside these ones. Please give me some advice for it. Thank you. So, like, depends what you need to know, right? So here, AI at Life, like, do you want to know exactly how they work, like internally, or do you want to use them properly? Because these two things are different, right? It's not the same thing at all. If it's the first, yeah, I'll drop it. Like, by the way, the book is completely available for free, I guess. So you can check it out. I bought it because I actually liked what they were doing. So for your case, at Life, there's really two things, right? There's like, I would say, knowing how to use ML properly, right? And then there's knowing how ML works, right? It's two different things. And I would say, how to say it without looking like a pseudo-scientist or whatever. What I would say is that this is a super important one, right? This is, I would say, plus. You should know how to use it properly, right? This is kind of good to know after you know that, right? So for example, for your stuff, I don't know what your PhD in machine learning is, right? Maybe it's like in computer vision, I would assume. So I would say that like you should be able to use these things, these models, in order to get to your research question, right? Like if your PhD is in computer vision, then it's a bit of a different kind of response, because you're gonna have to know it inside out in order to make your next model and whatever. But like if it's I don't know, I have no idea what is your PhD in. you got life, let me know. But if it's like in life science or stuff like that, and then you're using these models, it's a bit different. Like you need to kind of know how to use them properly and then apply it to your data. Like that is above everything else. You can have no clue how YOLO V12 is working and still get nice result, right? And then the results are good enough, and then you can move on with your life, right? And also publish some paper, but I want to go to the next step. Yeah, but like, what is your PhD on? Is it on computer vision, or it's like the application of computer vision? Because this my answer will be way different depending on like these two. So take your time. Yeah. So like, if your PhD is in like a field that use computer vision, I would say do that. Right? Do that first, right? Even if you have this hitch to know how they work, like deeply, like get better at this stuff. Like get better at like using it properly. Like look at more of these models, like how they are used. Look at like other paper that are using model that maybe you're not using, and then test it out, right? You have to remember that machine learning is an empirical field, right? What does that mean? Is that like for the thing, like from the day that this field was started, right? You do something, right? That can do something like that can get you to a good result, right? And then later on, what you do is you try to understand like, why is this thing working? That's what is happening. It has been happening in machine learning forever, right? Like the model is done, right? The structure is done. They messed around with different configuration and whatever, and then you go and you could do that because you can say like, my Wongi Bongi model has 85% accuracy on this benchmark, therefore it's good, right? And then it's a state of the art for now, and then everybody's like, why the fuck is it working? And you're like, I don't know, it's up to you guys to find out. And then like literally other people will start to study the model in order to understand why is it working, right? It's also why the field looks so complex, because you're gonna get like in this thing, like if we zoom into it, right, you see that it has like many different components in it, right? It's doing like weird things here, and then there's like this other thing that is happening, and the reason why it's set up like this is because it works, right? Like it's just working, and then like it's working and fantastic, like it's doing nice. But then like these people that are trying to study the model are gonna swap these out, right? They're gonna like say, hey, yeah, it's working, but it should be doing this instead because technically it's more optimal. They swap it, and then they're gonna get like a 2% improvement or whatever, right? They're gonna put a new name on this thing that they've done, or like publish a whole new model where the only difference is that thing, right? And then like it's gonna keep happening again and again. Like if you look, let's say ResNet, the number of variant of this thing is crazy, right? But like the initial version kind of just worked. They did something simple, it worked out, and it's fine. And then there were many variant that like they changed like again. Segment anything, same thing, right? In your field, like the first version was good, right? And then within a year, I think there's like 7 different versions of SAM that exist. Then it did SAM 2, and there's like already like 4 or 5 versions that exist that are just slightly different. There is some understanding when they make the model, but like it's not like they know everything that is happening. So if you go and try to decipher every one of the block, you might get at some point some part where you're like, I don't know why they did it like this. And the reality is that the other also kind of don't really know 100% why they did it like that. It just kind of worked, and that's that. Yeah, so you do this, yeah, you know how to use ML properly, and after that you go ahead and try to dive a bit deeper in knowing how the ML work. And while you're doing this, right, when you're diving to figure out how it works, keep in mind that some stuff are just there because it's there, right? Some stuff are just like this because if you don't have it like that, it doesn't work out, right? I have a good example of this in a recent paper that I've covered. Which was it? It was a Minimax. Yeah, this one. It's a huge one, like this paper, right? This Minimax scaling foundation model with lightning attention. Fantastic paper, right? Basically, what they did is they tried to make a linear attention like transformer architecture, right? That's what they were going for. While doing this, they realized that it kind of doesn't work that much well, right? If it's purely linear in the these layers, right? If like it's not just if they remove softmax attention completely and they just put like the what they call lightning attention, which is a linear type of attention, there is a reduction in the performance, right? So guess what they did? They just jammed softmax attention in there once every 8 layer. That's what they came up with, right? It's fantastic because the model works and it's good, right? But like if you're trying to dive deep into why softmax is required, it's not the right time to do it, right? Like it's not the right time to peek at the internal because they don't have that much of a clue. They just know that when it's not there, it's not working as well. When it's there, right, completely, it's working, but it's not novel. But then when they do like 7 stack of lightning attention, 1 stack of softmax, it's fantastic. It has all of these nice properties. Okay, so rant over for this. But if you want to learn of how the stuff works inside out, right? The best way is 2 things. You go and then you try to like what I like to do is try to you do a small course at the beginning, right? It's a small course to understand like the basic of machine learning and how the inner thing work, and then you go and try to implement some of the bits yourself. We try to make like a feed-forward, fully connected feed-forward neural network. You do it and then you check each of the component how they work, right? And then you try to go a bit more complex. At some point you're gonna hit PyTorch, and what I like to do is I like to look at the most impactful architecture. Let's say pick ResNet. Let's say you're doing computer vision stuff. You pick ResNet and then you look, you go there, you read the paper, right? And then just go and look at the literal PyTorch implementation, right? So you go over there, right? And then you go view on GitHub, right? It's gonna go in there. And then you try to understand what the heck is happening on this file. That's it, right? And then you go slowly on the file. And like there's a lot of stuff in there that is not important for you because it's like PyTorch internal that you should not even look at. But some bits in this thing are gonna tell you so much about like the connection between the paper, how it was made, and like the stuff. For instance, like you can see at some point in it, like the little change that they made. Where was it? I think it's here. You're gonna see the little change that they made that like brought back the X at the forefront, right? And that's it. That was kind of the whole thing. Like there's a connection between like the X with the thing that is happening after the weights have gone through, and this is how they're like learning the residual. But when you see how simple it is and you read the paper, you're like, okay, right, that's it. You get it. Yeah. And yeah, check out the ResNet collection. I think you have that, right? Oh yeah, right. Yeah, you can do that too. You can study ResNet straight in there. Yeah, so that's kind of my 2 cents on the topic. Is like you understand heavily how to use it, and then you try to understand how it works by looking at the internal. But keep in mind that like some stuff in it like is wild. Like you see how much the author don't know what is happening when you read the old paper, right? If you go 15 years back and you check like at the seminal paper and then you read it, there's so much stuff in it that is not that accurate, right? Because they was the best guess at the time. There's some stuff that is like crucial, but some other stuff like, yeah, no, after that we realized that like it was not how it worked and this is that. It doesn't mean that the model is absolutely useless. No, it means that it was good and there's some truth in it, right? Because it was useful, but there was other ways of doing it. Yeah, and after that you see, I think I'm going to show you this. Architecture. You're going to see like sometimes it appear in very subtle ways, right? Like you see here, right? Look at this. You see this little thing, and then it goes over here, right? Like this is ResNet. Like that's like the residual connection of ResNet that is happening right there. Like ResNet is not super the cutting edge at the moment, right? But like there was an idea in it that was super important, which is the residual connection, which make the effective length of the network a bit smaller, right? There was a whole bunch of study about that, but this little connection had an impact because now you see it in different architecture, right? But if you jump in here and you try to understand like why is it like this, it might be kind of difficult to comprehend. So yeah, try to understand how to use them first. It's an empirical field, so you need to kind of get your hand dirty, and after that, like you go in and you dissecate a bit like each of the little component. Absolutely agree, computer vision, and for me in particular, meta learning. I'm going back to the books before applying for a PhD. YOLO, apply for the PhD first. Yeah, that's it. A PhD, honestly, you like when you're not in a PhD, you don't understand how like the actual thing. Like when I applied for it, I already had a lot of research background, right? When I applied for the PhD, I thought like kind of had to like build up on what I knew before, but the actuality was not this. Like the actuality is that you're gonna be in a very pointy edge of a very like of one thing, right? And you're going to be so on the pointy edge of this one thing that you're going to become the de facto expert because no one know the combination of things that you know in order to make this work, right? There's very few people that will be able to help you. Even the collaborator or your PI won't be able to help you that much because you're kind of in uncharted territory. So in any ways, it's not like you need to know like everything and be a master on the field, right? That's not the point. You're going to be a master of the combination of skills in order to answer your question. That's it. Like that's the PhD in a nutshell, right? You might be absolutely terrible at like a whole bunch of things into like the core field, but because your stuff is requiring like 5 different other things, you're gonna be like an expert, a de facto expert. You may be a poor expert if you don't know what like have a lot of clarity about how to combine these different things together. But if you're smart enough and then you read a lot and then you have creative ideas, you don't need to be like a super expert in like everything that you're touching. You just need to know how to recombine them properly. You should check it out instead of reading Wikipedia for which book? I think you're talking about the other book, right? Yeah, I should maybe check it out. Yeah. Yeah, no worries. If you have any other question, don't hesitate. Maybe I'll have time to finish this thing today. Okay, so if we go back here, we have R0 is sufficiently small and return X0 as the result. I don't get it. Like I don't. Maybe I'm kind of dumb right now, but like, it seems to me that this is and this is not the same thing. I don't know why the AK is different. Maybe it's a typo because everything else is similar. I don't know where the R is coming from. in that front. And I would assume that the guy that made this thing, who was it? Paddy Wardle, that dude took it from here, the algorithm, because everything else looks similar, even the ordering. Is it the ordering that is similar? Yeah, I think it's pretty much the same. Okay, so I would assume, right, that this is right. I would assume that this is right. And if it's not, I'm going to be able to switch it a bit. Okay. Okay, cool. Yeah. Okay, right. You see, they repeat it this way. They repeat it with the RK. So maybe this is just not right. Okay, yeah, that part, I'm gonna just put some asterisks on it. Oh, okay, that's what you meant. I'm just gonna put that over here. Take that, minimize it a bit. I'm just gonna jam it here and save. Oops. What's up with PK in there? Okay. Do you have a PDF version of the book, or like, can I just I'm not gonna pirate it. It's numerical recipes, right? Okay, I think I found it. Do I have the right to look at this right now? Conjugate reason 500. Let's go. Dude, this is 1,000 pages. What the heck? Okay. Oh yeah, they're using RK, same. Okay. Let's put it here. Let's Google it. It's free. Show some nag when you read the PDF. Yeah. Well, I just found a PDF. So we're over here, and then it's saying the same thing, same thing here. AK is this, RK. So I guess maybe they fucked it up. It's very possible. By the way, there is nothing as frustrating, right, as being in a pointy subject, right? So what I mean by pointy subject is like you're kind of alone on this, and then you're working like with very few like rarefied information about your stuff, and then realizing that something was wrong in an implementation. If you're doing a PhD or like you're doing research, you would be astounded about how much it happens, right? I remember like I was implementing something for one of the study where we're trying to put the functional connectivity graph of the data that I had for amplitude for the amplitude data of the EEG signal or like the phase. And at some point I realized that there was a mistake in one of the code that I took from like another lab, and I had to fix it up, right? It didn't change the stuff immensely, but it creates this sort of anxiety about like, is my shit correct? Right? Is my stuff proper? Or like, is there a big mistake in it and I don't know? Sometimes there's a mistake and it doesn't matter. So it just kind of works still for some weird reason that you could derive, and then you're like, yeah, it still works. It's not the same thing that you're saying, but it still works. Other time, it breaks the whole thing completely. And like when it's rarefied of information, okay, because there's not that much people that think about this stuff online. You're playing with like a very few data points. So when it happens, and I learned it like after a few years of doing research, just like send an email to the guy that made it, right? And then have a discussion with them. That's the best way to get it done. If you're an introvert and you just want to be in your lab and doing your own stuff, like you might not like be thinking about this, but you have the right to go and ping the guy or the woman that made whatever you're using, especially if like it's basically you two that knows this are using this stuff. Okay, cool. So okay, I'm gonna trust this more. So from now on, I'm not trusting this because the Bible said no, and I'm gonna trust the RK. So I'm gonna be doing RK there. Okay, and then I think okay, the rest is what? The rest is the same. And okay. And then this is a bunch of proof, I guess. Right. Okay. So if I want to go straight, I think I'm good. I think then I'm good to go. The alpha is this. My beta is it the same? RK plus 1, RK, this is transpose, divide by this, okay? Same shit. Yeah, same stuff. Okay, cool. Perfect. Okay, folks, I think we're ready to code something. let's go at it. I think we're right. I think we're good. I'm gonna do first the initialization, right? And then I'm gonna do a dummy thing over here, and then try to go into the return over there. I think we should be good to go if we do it like that. Just gonna clean up a bit. Good. This is good. Okay, perfect. So one structure will be the initialization. Can you see my stuff? Yeah, okay. And then after that we have the iteration. And finally we have the return last resort return. Oh, cool. I didn't know about this book, to be honest. It looked pretty solid. Yeah, you're right. There's a lot of there's not a book I was reading about the scientific computing, but this looked pretty awesome. I don't know if it is the third edition that is the most up to date, but I'm gonna take a note of the bookmark. To check it out. Yeah, definitely. So last resort return, and my return was gonna be my solution vector, and here it's this. This is the thing. This is the solution vector. Yeah, but wait. So this is x0. This is actually x0. I don't like. I don't like just x. I would say guess. In physics and chemical. Ah, okay. It's older than the M of this, yeah. But you see, like this stuff is like has cycle, like a bit unrelated here, folks. But like in machine learning, usually there's gonna be ideas that are very old that just come back and now they work, right? And before they didn't work, but now they do, right? Like if you were to look like 3 years ago, like, and you were talking about reinforcement learning, people were like, yeah, it's cool, but like it's not that, it's not the thing that will get us to whatever we're trying to get as a field. But now reinforcement learning kind of came back in the forefront, specifically because it's used in the post-training a lot for aligning the models to whatever you want them to do a bit more. So there's always, I would say, a good incentive for you. Like, as soon as you know how the stuff works, there's always a good incentive for you to go back to the basics, right? And go deep into the thing that you feel is most interesting, right? Go deep into whatever, like these type of optimization techniques, or like a very specific type of algorithm, because like the ideas are getting recycled again and again in different combination in machine learning. It's just how it goes. Like the cycle kind of keep on going. If you look at all of the linear attention algorithm, right? And you look at them very, very closely, they all start to look like they're building an RNN, right? Which is very interesting because RNN were used before transformer was set up, and it's linear. It doesn't have the quadratic complexity of like a transformer. It's linear. It's a bit slow to train, and it's overriding a bit the memory from the first token to the last token, right? But when you look at how like a lot of people were trying to transform the self-attention layer of a transformer, they're kind of trying to go back into an RNN. And sometimes this is what happened. Like they literally went back to an RNN. They were like, hey, we solved that in linear time. But then they made it in a way that like they could train it in a kind of transformer-ish way. And it has some usage, right? But like it go back to previous ideas that was already kind of thought about, right? This is also like why the meme, for sure. You're sure you know this guy, like this dude, right? Like whatever you guys are gonna invent in machine learning, even if you're doing a PhD, this dude already done it, right? He already done it in some shape or form, way back in the day, in like an obscure paper that you have no clue about. But it is true. When you look at it, it kind of had the shape right. Even ResNet, like, if you look at this dude is always before, always before everybody else. Like this dude, right? Look at the timestamp. The highway network, right, is not used at all right now. Absolutely not used at all. I don't think we have a good visual of like what the actual thing is. But it is exactly the same idea as ResNet, as like a residual connection. It made it more like a LSTM, like a long short-term memory kind of thing with different gates. But it is a superset like of ResNet. And ResNet was, I think, published 2 months or a few months after that, right? And it actually referenced highway network. But like he did it before, but it's not the thing that is remembered. We don't say a highway network. We said a ResNet network, and then all the variants are on the ResNet architecture. But it's just an interesting thing to keep in mind. If you feel like you can't keep up with the cutting edge of the field, I would say it doesn't fucking matter at all, because most of the ideas that where they're going for are kind of useless, right? Some will be a breakthrough, and then we're gonna move forward. Let's say reinforcement learning to make a model, large model, reason. Very good idea. This will stay like forever, in some shape or form. But that's what you have to think about. So what it means is that yes, you have to keep track of like where the different ideas that are in the forefront, but don't if you're really interested in theory, go back to the old stuff, right? And look at the old stuff, like play with it a bit, And then like as soon as you have a few of them that you can understand like intuitively how they work, you're gonna see some of these patterns happening over and over again. Okay, cool, perfect. So this is the good, and then we initialize. This is this check mark. We're done with this. Okay, we already done that, and then we have to make our residual vector. So and then we have to make the residual. Just have to put it into the right shape. Beta minus a dot product. Okay, so it's gonna be beta minus a. I always forget there's the at. I think you can just do that. Okay, perfect. And we have, what was this stuff? It was x0, so it's our x guess. This is our residual, and then we have p0, which is, I will call it search selection. I have a tendency to prefer long names. Sometimes it's a bit ridiculous, and then I'll just like refactor them. But I much prefer having super long names that are descriptive versus anything else. Okay, cool. So then I can just have my iterations here, and for I in range, well, k, right? K in range. We have n, yeah, and then I'm just gonna print, do nothing. And that's it. And then I'm going to use a search direction. This is my residuals. This is this. So this is also our 0. And this is our P0. And that's that. And then the tolerance is what is useful. So my exit criteria will be calculating magnitude okay, alright. Okay, and this is how I'm gonna get my residual. So I'm gonna get my mag residual, oof, and I'm gonna put my residual here. And if this is my exit criteria, early exit criterion, mag residual is smaller than my tolerance, I'm gonna return my x guess here. Okay, so we're getting there. Okay, I'm just gonna print it here. We're gonna still doing nothing right now, and then we're gonna print the residual. Put a nice string here. Okay, we got this does work. What's up? Okay, that's perfect. Good. Good, 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 good. So we're getting there. So we got that done, and we check for convergence here on the residual. Do we need to keep track of more than one version? No, right? We have RK plus 1, RK plus 1. Oh yeah, we do. Okay, what I'm gonna do, because this is the next one, and I need both of them for the B, and I check the convergence on the next one. Yeah, okay. So here, this is gonna be okay. Next residual for now is this. Do change, please. Please, for the proper implementation. I take this, and this is what I'm gonna do it on, and I'm gonna call it my next residual, right? And then here, my residual will become my next residual. Right, because this is okay, this is good. Got that. And I can calculate this, then I can calculate my beta. So here, calculate beta. Okay. So this is not part of the early exit criterion. This is. And here, I'm gonna calculate the next K. So the residual at K plus 1. Okay. So we have to do that. And then we're gonna calculate the beta at K, which use the 2 residual. And then we're gonna calculate our next. Right. Calculate next search direction. And do I need, I don't need the, no, I don't need to keep that. This is good. Yeah. I update the search direction, update the residual, use both. I need to next one for this. Yeah, well, this is good. So this is where updates. Could also keep track of everything, but I don't need that. Now be K plus 1. Okay, and then the search direction also. Okay, search direction. Okay, wait, do I need that? PK plus 1, it's not needed anywhere. I just can calculate it here and it'll be done. Okay. 0 to do calculate. I'll actually just put it -1. Get the next search direction. Put it in PK. So here, okay, that's fine. Then I need that, the alpha. And for this, okay, this is good. Calculate the alpha. Okay. Okay, okay, perfect. So we're going to do RT, right, T, which is actually called the residual because I wanted to call it that. Okay, divide by pk transpose, so search direction t pk search direction. Okay, should be good, and this is our alpha, which I will call step size. Correspond to A. Okay. Right, and then we can calculate my new guess here. Calculate new guess. Okay. So, do I need to overwrite it? Do I still need my xk? No. Okay, perfect. So it's gonna become x guess equal the previous x guess, which is x guess minus what? No, plus step size pk, which is our search direction. Okay, so this is xk plus 1. Okay. Be helpful to add some assert for the shape route. Absolutely, yes. It would be very useful if I was not that's it. If this was kind of production stuff that you were trying to use. Yeah, definitely. Like that's kind of how I would do it. I like to do it like a very like scaffolding it. If you see right now, I'm not doing anything linearly, right? I started with the top, I did the end first, and then I'm like hard coding a bunch of stuff right now. But yeah, if you were to do it like to make it clean, you can put a bunch of assert a bit everywhere to make sure that like the shape is always nice. Okay, so this is k plus 1, and we check the convergence. So technically, like convergence with the rk plus 1. So I kind of have to calculate rk plus 1. So this is the residual, right? Plus, no, minus my step size at A in my pk, which is my search direction, right? So I was saying, yes. Okay, so this is what's up over here. I'm going to just put that in bracket. So here, this is our k plus 1, right? Okay, so I think we're getting there, and we need to keep both. We check for convergence, and then we calculate our beta. So our beta here, what is the beta? What's the name of this thing? The new direction scaling. Oh, beautiful name. So new direction scaling. So okay, so next residual. Oops. D. Okay, yeah. Wait, I'm just gonna remove that. Okay, so add next residual. Divide by, what are we doing? Okay, same. Okay, that's the previous one. So it's the residual now. Residual t at residual. Okay. Put a whole bunch of bracket in there. Sure, everything is well insulated. Bracket here too. The form. Okay. So should be good. So this is beta. Beta. Okay. And we update that with our, this is our search direction, right? So our search direction is next residual plus our next new direction scaling, and that was the previous one. So search direction. So this is pk plus 1. Okay, did we fuck something up here? I think we're good. If let's do it, just sanity check. So we're going here and doing that, right? Should be good. And then we're doing the p0. Okay, cool. Alright, this is our p0. And then we're doing the little step. So alpha is RK, so this is good. Residual transpose dot product residual divided by the search direction transpose. Okay, dot search direction. Okay. Oh, that's a good question. Yeah, you have to kind of do it and do it by hand, and then like set up the test cases in order to understand what's up. I like to use the test cases of the platform directly because then like you already have the answers. Yeah, but you have to set up your own kind of test, and you have to remember like when you're gonna do your test cases for this specific thing, it need to be symmetric and positive definite, right? So you have to kind of orient it properly here. Yeah. So like it's kind of why I like this, right? Because like I don't have to do it and like set up my own kind of test cases because it's already kind of done for me. It's already kind of validated, so I can trust it a bit more. Than my own test cases, and I have to understand it, like if my stuff was proper and stuff like that. Yeah, that's kind of one of the reasons why lead code is so useful, because like, you already have the solution and a whole bunch of like different type of input, but this is more like algorithmic, so it's kind of nice. Okay. So you can also take something from a textbook, right? That would be cool. Like if you already have a textbook, you like just jam them all, but you have to find one that has like they implement the conjugate gradient by hand, and then like it show you that the test cases and the result that you get. Okay, we update the residual next. Okay, our guess. Wait, so our guess is a previous guess plus a dot product p step size dot product search direction. Should be good. We have a next residual, which is the previous residual minus step size search direction. Okay, so it should be good, and then we keep the two because we need them for the beta. We check for convergence next, right? Magnitude of the next residual there, and then we're gonna log it. But if the magnitude is smaller than tolerance, return the x guess because the x guess was good enough. And then we do our beta, which is our next new direction scaling. and then it's like the transpose of the next residual, transpose this, divide by the residual previously, and then that, and then we update our search direction, and then we have our next residual plus the new direction scaling plus the search direction. Okay, so that should be good. And lastly, to not mess it up, we put residual as next residual. Is there anything else I need to put there? No, I think it should be good. And then as last resort, when we're done, we'll put the XGS there. Okay. I'm gonna actually, well, it should be good. I think that's, let's see. Oh, it didn't work. Of course. So what's the value mathmal input operator 0 does not have enough dimension as 0, blah, blah, blah. Okay, where did it mess it up? Oh shit, I don't know. Why did it mess it up? Is it like this everywhere? Yeah, it's like this everywhere. Okay, wait. Did I don't even need the K. Okay, it doesn't matter. Okay. If only, if only we put some assert over okay. So input operand 0 does not have enough dimension. Something is completely, is like literally nothing. I'm not sure which one is it. Is it my XGuess that is completely messed up right now? No, it shouldn't be. It doesn't even go there. Okay, maybe it's this one part that is messed up. Wait. Yeah, we need these assert. Let's run this multiple times. I'm not even going there. Wait, what the heck? Can't even print. Wait. Is it because I didn't save? Okay, wait, I can go there. I output that. Right? So will it just run if I only have, okay, no, I can't use, okay, I get it. I can't use, if I have an error, it will just tell me the error and not the output. So I have no clue which part is actually fucked up right now, which is not that fun. So I'm okay, let's step through this. We don't have a debugger in this thing now. Okay, I'm just gonna put it here. You're about to see the ugliest ugliest debugging that you ever saw, right? Debugging in process. Okay, so let's check it out. What's up? Perfect. We're just debugging this and nothing happens whatsoever. And now we're stepping once. Let's see if this thing is messed up still. And no, it's not this one. Except if we're changing stuff up. So is this will just help me for the first run. It seems to be that part because I'm doing a dot product with something that is not. Okay, yeah, that's fucking dumb. Just need to multiply. And that should be good to go here. Yeah, that's good. So I'm doing the same dumb shit here. He should be doing the same dumb shit here. Okay, perfect. So this is a step size, so this is multiplication, right? And we're doing that stuff here. Well, it doesn't matter if this one is first or the other one. Yeah, it absolutely doesn't matter. So it's this, this, that. I don't like it. Like, okay, I'll just put some parentheses here. We could try out the generate int. Maybe you can't tell. Maybe try to print the sensitivity. It's capture the prints. Yeah, I'm starting to see in the output, but like it was fucking up here in the step size because it was actually like the matmul. I was trying to do a dot product with like a scalar here, like a genius. But that this should be still good. Like this should be good. I think like the output is overwriting my print statement. So yeah, maybe if if I'm a bit more directive in how I'm printing it. But this is good. Okay, I'm getting there. I can calculate this because this should not do any harm. Theoretically, it should be good. So we're getting there. I don't need to print this anymore, and I can just format this a bit. Is it going down? Residual is not changing because I'm not doing anything here. The new direction, and this. Okay, wait. That's a scalar. This is a multiplication, and this should be good. So the magnitude should go down. Okay, well, that's good. So if I remove that print statement and return my guess, got it. First try, guys. Oh, geez. Yeah, actually, that was it. Yeah, it was not that hard. The only thing that I messed it up, honestly, was this. I did a dot product with the scalar, which makes absolutely no fucking sense. Yeah, so we actually got it first try. It was that fourth try. I didn't press this button 100 times. Just did it once. So yeah, to be honest, it was not that it was not that difficult. But like understanding, like the algorithm is not too hard because like the shape is the same. If you look at any gradient descent, like it will, like even if you look at stochastic gradient descent, it will have the same form, but some element will be a bit changed. If you actually look at momentum gradient descent, Python, I guess you'll find that. Yeah. You're gonna see a similar form. Yeah, here. Yeah, look at this. Right. You see the form that I'm talking about here? Yeah, you need to make it harder. Like that was too easy. But to be honest, like for this mode, I can implement it. Right? If you ask me to explain, like. Why the A is like this and why the beta is like this, it still will take me an hour in order to figure all of the details out. But the shape is the same. Like if you look at the shape like this and you look at something with like that, it's a bit simpler, like the momentum gradient descent. it's not that wait, this is the momentum one. I think this is just a normal gradient descent. But you see the same shape. You see here, over there, like it's a kind of a similar shape. You're doing this multiple times. You have a number of iteration, and then here you see like here how we're doing our like guess. There's still the concept of gradient that is in there. There's our step size that is in there, and we're evaluating our stuff, right? So this is like the gradient descent, the normal one, and I believe at the down you're gonna see the momentum, right? So you see, you just do a little change, right? Here the momentum is over there. I just wanna keep it. Yeah, you see here the momentum, and then the momentum is here, and you calculate the momentum. I don't see where they're calculating it, but there's some aspect of, okay, so it's a hyperparameter. There's some little thing that is added, and then like the overall shape is the same, right? The overall shape doesn't change. So it's kind of the same idea. So like if you see here, there's like two kind of parameters, like bigger parameters that are like helping you out define how you're gonna move through that plane. But this idea is like everywhere. Like even if you take a look at Nesterov, if you take a look at Adam weighted, it's all the same shape with like some of the parameters that have a specific definition that are in there, and that just guide your movement. So we have a few questions. When you practice this problem, what's the best takeaway besides knowing how to implement the recipe? I feel like the exercise really tested your skill of reading source, then implementing code. You would be surprised how most machine learning and deep learning stuff, it's not about the implementation. The implementation is kind of like, bleh. Like it's not like some crazy like software development like a behemoth that you have to wrangle. Like if you take a look at the code crafter stuff that you were talking about like building something, it's a compiler, right? Or you're building like I don't know, like a Shadow DOM engine, right? Like these things are kind of a logical beast, right? Because you have to have multiple layers of abstraction that is working properly together in a specific way in order to make it work. And if there's a bug in there, it's going to be a mess to kind of figure out where it goes. Anything machine learning or deep learning algorithmically related, I never saw any implementation of it that was like very verbose, right? It's all fairly condensed. And even when you're looking at the architectures, right? The architectures are well bounded. Like it's really like putting Lego blocks together, right? And if you need to understand like one of the Lego block, you go in there and then you read the stuff and you try to understand the mathematical notion that makes this true, or like make it a bit better in the particular setup that you're at. This is also why when you see like the research applied to like this architecture, they might single out one of the layer, right? Let's say RMS prop in the transformer, like they single this out and then they change that part out. And then this thing could make a new architecture or something like that. Or you can mix some blocks away, like I showed you with that paper, right? Like if you think about it, like the mixture of expert here is not some outlandish stuff that is difficult to understand. It's a feed-forward neural network, right? Gated. It's like the implementation here. Yes, if we're talking GPUs and like optimization here, yes, it's a bit more involved. But the architecture is not wild. Like look at this. It's like a bunch of these ones, right? You have a router that will take two of them, and you're gonna take two of them, and then you're gonna add them up, and that will be the output of this layer, right? But like each of these components, when you're gonna check them out, you're never gonna feel like you're entering like a full code base and you're like, what the hell is happening? It's all the insight, and then the interesting thing about machine learning and deep learning is always outside. It's with the data, or with like the statistical effect of whatever you implemented in this given part, given the data, and then like the overall, the rest of your structure. Like here, right? The interesting part is not any of these individual components, right? Even lightning intention here, like this linear type of intention, is not that interesting in and of itself, right? What's interesting is that when you mix these two together in some kind of recipe proportion, it leads to something good, which means that like, even though you have a quadratic a penalty here in complexity, there's something useful here. There's something about looking at all of the token, right, with all of the other token, that is important, that you can't really replace in order to make transformer robust. Yeah, right. But like each of the components are not that complicated whatsoever. And as soon as you're gonna pop one out, right, and then take a look at it, you're gonna realize that. But like you said, the important thing is what an hour and 30 minutes I did at the beginning of trying to understand what the heck was going on here, right? That was important, and you get to that level of looking at it and like understanding it, I feel, when you start to implement it. When you start to implement it and you try to really understand it, you're gonna see that sometimes, and let's say a lineage of techniques, right, that kind of build on top of each other. The first one you're gonna implement, you might not understand everything. You might be like, okay, yeah, I understand the rough structure, but these bits I don't know. And then in the next iteration of this lineage, you're gonna see that like, okay, they changed that and this had this effect, right? I understand a bit more where this is coming from with this new explanation, right? That's kind of something that is super useful. At some point, you understand deeply why this stuff is working. For instance, for me, like momentum, at the beginning, I was like, what the heck are they talking about? But because I've implemented like the different type multiple times, and I see like how useful it is over and over again, I kind of got an intuition that like, yeah, momentum is something that is important in various different shape, but it has something about, it holds something about the learning that is absolutely crucial for finding a local minima, right? I hope it helped. Let me know if you have other question about that part. Okay, we got this one. So I think that's pretty much it for today. Yeah, like I said, don't hesitate to go over there, DeepML, to check them out. Keep it up, folks. You're killing it. I really like this. I kind of wish there was still more exercise. I don't know, like if people could contribute and stuff. I need more. I need more of them. But it's good because like there's a good spread, I would say, between like the medium, the easy, and the hard ones. Yeah, try to get a bit more hard ones. I like the challenge, right? Especially if they're a bit more esoteric, right? Like the archaeological aspect of it is pretty fun. So with that being said, I wish everybody a fantastic beginning of the week, right? Have a good one. Don't forget to keep digging into machine learning, deep learning. I think it's honestly, I think it's like a skill set that will become more and more important in the future. Like to be able to understand and to be able to like gain more than like a surface level intuition about how things are working, right? AI is like is being added to many applications. So yeah, I think you should dive deep. You should go deep, right, into machine learning and continue studying. And Zadlak is saying you should look into the book Understanding Deep Learning. There was a YouTube series implementing the solution. Nice. I didn't know about that. We'll check it out just after this. Oh yeah, I know about this book. Yeah. Cool. Yeah, so much good stuff out there, honestly. Like the amount of material that you can get your hand into, like in current age, that is high quality, right? Absolutely fantastic. You should, you have no excuse, like to not study this stuff and understand it. Yeah, I love this shirt. Going deep. All right.